Welcome to Tom SciCast. This is another episode following along with my Bio for Health Science classes. So the topic today is going to be how elements combine to form molecules and compounds. Now, typically this is a heavy chemistry lecture, and I've been teaching this for 20 years, and I can tell you that for some people, chemical bonding is just hard. So we're going to get through this. I personally really enjoy thinking about how the bonds that hold the world together work. And these chemical bonds that we are going to discuss today are going to include covalent bonds, both polar and nonpolar, ionic bonds, and hydrogen bonds. And of course, there's also metal bonds for all of you chemists out there, but we're not going to get into those today. Okay, so here it is. Elements, they're going to combine to form these compounds and molecules. So a compound or a molecule, they actually have emergent properties. So remember, we go back to a previous lesson. They're going to have properties different elements that combine them. So take sodium. I mean, this is a metal that catches on fire in water. You combine that with chlorine. Yes, a toxic gas. You do not want to breathe it. You put them together, they form an ionic bond, and you get table salt, known as sodium chloride. Okay, so there's other ways of looking at this here. To understand how these chemical bonds work, we need to just refresh a little bit on the atomic structure. Remember, protons, neutrons, and electrons are the subatomic particles that make up an element, or make up an atom to be specific. The protons and neutrons are in the nucleus of the atom, and the electrons, of which there are an equal number of electrons compared to the protons. Did I say that? Yeah, the protons are going to equal the electrons in their numbers, and they're going to be in these shells, and this is where you find the electrons. Now, importantly, there's some properties about these electron shells. The first one only holds 2 electrons. That's it. No more, no less. Or to be chemically stable anyways. And then the second shell and the third shell as well, they hold up to 8 electrons. And then whatever your outermost shell is, that is called the valence shell. And inside that shell are the valence electrons. So the valence electrons in the outer shell. And these are really responsible for forming chemical bonds with other elements. Yes, it gets more complicated than that, but for our purposes here, we're just going to stick with this. Okay, so, table salt, that's a compound. We already talked about it. It's a pure substance made of 2 or more elements in a fixed ratio. And then a molecule. A molecule is made of 2 or more elements joined by chemical bonds. And usually when we think about these chemical bonds, we're thinking of covalent bonds. So I've got 2 molecules. I did not randomly pick them. I'm going to use them to make some points here. But I've got methane and water. So water and methane, 2 very different types of molecules. So they're held together by these things called covalent bonds. Okay, valence electrons, valence shells, covalent. Co means with. So they're sharing these valence electrons to become chemically stable, because that's what elements want to do. They want to complete their valence shells. So if you look at water, water is a H2O. So you got a chemical formula, and that chemical formula, H2, tells you there's 2 hydrogen atoms attached to 1 oxygen atom. Now, hydrogen has 1 electron, right? It's only going to need 1 more electron to complete its outer shell. Remember, hydrogen is element number 1. So we're talking very simple here. 1 proton, 1 electron. And that's it. Now, oxygen has the atomic number 8. And most of them are, oxygen 16s. They got 8 neutrons in there. But oxygen with the atomic number 8 means it has 8 electrons as well. 2 in the inner shell. That means it now has 6 in the outer shell. All right. So it needs 2 electrons to complete that outer shell. So what you do is you share your valence electrons. So oxygen, atomic number 8, it's got 2 electrons in its first shell, 6 in its second shell. Hydrogen only has 1 electron. And then you combine them, right? You start sharing those unpaired electrons, and you form a covalent bond. There's some really cool stuff for those of you interested in like PChem and things like that, some of the quantum tunneling that occurs to get these things to work. But beyond the scope of this class, but in the nutshell, there they go. You can see the hydrogen. I'll use my laser pointer function here. Let's see if I can get this to work. Oh yeah, laser pointer. I feel so sophisticated. But there's our bond right there. There's our unpaired electron from hydrogen. There's our unpaired electron from oxygen. Stick them together. I got my bonds, right? I got a covalent bond by sharing those electrons. Turn this laser pointer off and go to the next slide here, right? So now water is chemically stable by forming those covalent bonds, right? By sharing their valence electrons. So there we have it, hydrogen has 2 and oxygen now has 8, and this is a happy element or a happy molecule. It's very stable. Okay, it now has a total of 8. Now, these are 2 examples, oxygen and hydrogen. There are other elements out there. And for organic chemistry, when we start talking about the chemistry of life, 4 elements make up like 96% of you, right? Hydrogen, carbon, nitrogen, and oxygen. And they have each have a different number of covalent bonds they can form. Hydrogen, you got 1 electron, man. That's it. You can only form 1 covalent bond. Now, carbon is the element 6. It means it's got 2 in its inner shell, 4 electrons in its outer shell. They're all unpaired. So guess what? Carbon can form 4 covalent bonds. Nitrogen, we're going up. 1 more proton, element number 7, right? So 7 electrons. That means it has 5 electrons in its shell, and it's going to form 3 covalent bonds. And we just did oxygen, and it forms 2 covalent bonds. Okay, now, importantly, this is very important because you might have noticed water and methane, they're both being held together by covalent bonds, but water is a liquid at room temperature. You throw a match in water, nothing happens, right? The match goes out. Methane is a hydrocarbon. It's made up of carbon and hydrogen. It is a gas under normal room temperature and standard pressure and temperature, right? It's a gas. But if you have a room full of methane, don't light a match, right? Because it will explode. There's some differences there between these 2 compounds here. Between these 2 molecules. So before we get into why water is liquid at room temperature and why methane is a gas at room temperature and one's flammable and one's not, it turns out that there's differences in those covalent bonds. See, not all covalent bonds are the same. And this comes down to a property called electronegativity. Electron, right? Electronegativity is basically the ability of an element to attract electrons, okay? So electrons are negatively charged. Protons are positively charged. Opposite charges do attract. So the more protons you have, the stronger your charge is going to be. So the more protons you have a stronger positive charge in your nucleus. You're going to have a stronger pull on those electrons. But there's one more variable. It's not just the number of protons, it's also the distance to the nucleus that matters as well. So if you take carbon and hydrogen, 1 proton versus 6 protons, they actually have really similar electronegativities because that 1 electron is much closer to that 1 proton, but in carbon, you're in the next electron shell, is further away, so they have similar electronegativities. And in fact, nitrogen, going from carbon, with 6 protons, and nitrogen with 7, nitrogen is more electronegative than carbon, and oxygen is more electronegative than carbon, hydrogen, nitrogen, and hydrogen. Did I say that? I got lost up there. In fact, oxygen is the second most electronegative element in the universe. Now, if you know the periodic table, you're probably going, well, what about sulfur? Sulfur is just right below oxygen on the periodic chart, and it's also, it's got more protons, but you've got 3 electron shells, right? So the valence shells are even further away than they are from oxygen. So sulfur has less of a pull on its valence electrons than oxygen does. So oxygen is the second most electronegative element in the universe. Fluorine is, of course, number one. Okay, so we look at water. Water is forming what we call a polar covalent bond, and methane is forming a non-polar covalent bond. And whether or not a bond is polar covalent or non-polar covalent depends on the electronegativity of the element. Okay, if I've got two elements like oxygen and hydrogen bonded together, oxygen's way more electronegative than hydrogen. So as a result, the electrons are not shared equally between these two elements. And in fact, oxygen has a stronger pull on the electrons. The electrons spend more time near the oxygen, less time away from the hydrogen ion, from the hydrogen end. And as a result, you gain the molecule becomes polar as the oxygen becomes partially negatively charged. That's that little delta symbol right here. Oh yeah, highlighter. Let's try this one here. There's my delta symbol. That's partial negative. Down here, partial positive. This is a polar molecule. Okay, now I actually have to turn this off to advance the slides here. I'm still learning how to do all this fancy stuff here. Okay, so polar and non-polar. So water is polar. So those water molecules, that partial positive end is going to attract the partial negative end. They're going to be stuck together. We're going to come to that. It's called a hydrogen bond. Now we look at methane. Methane is got non-polar covalent bonds. That is because when we look at the bonding right here, this is our covalent bond. Actually, let's do a little highlighter right here. Here's our covalent bonds right here. What's going on is that we're sharing these electrons equally or nearly equally. So the electrons are about equidistant between the hydrogen end here and the carbon end. This is a non-polar molecule. There's no partial positive and negative charges on it. Okay. Now also, because they're sharing the electrons equally, for those of you interested in chemistry, I started this lecture out and I said, hey, water and methane are a little different. The difference here is that's a weaker covalent bond. It's easier to break. You take a spark or a match, that's all the energy you need to break that bond, right? So we'll come back to that. So that's in a nutshell, the polar covalent bonds and non-polar covalent bonds. Okay. And the reason why this is a gas at room temperature is because it's not attracted to any other methane molecules very easily. There's some weak van der Waals forces, but not enough to make it a liquid under normal standard temperature and pressure. Whereas water, those molecules are attracted to each other. We're going to come back to that. I always get a little ahead of myself here sometimes. I get wound up and get excited thinking about bonds. Ionic bond. Reminds me of like James Bond, right? Okay, in an ionic bond, these are different. What you've got is a really big difference in electronegativities and number of valence electrons. So if we come over here, let's take a look at, let's do a pen. Okay, this is sodium. Now sodium is element number 11. So we got 11 protons, 11 electrons. Here's our 2 right there in the inner shell. And then we've got 8 in the second shell. And then we have this one little lone electron out there. That's chemically unstable, right? Now, chlorine over here. Chlorine is element number 17. So you get the idea. We're going to have 2 electrons there. Sorry, I can't really draw really good in my mouse. We got 8 in this shell right here. That's 10 plus 7 more electrons. Okay, so chlorine only actually needs 1 more electron. But if you notice, 30 electron shell in sodium, and then we get a 30 electron shell over here in chlorine. Now, so these are equidistant in their outer shell, right? But chlorine has 6 more protons than sodium. So it's way more electronegative. So what happens is it just basically takes this electron, it snags it, it comes over here, and now it's got 8 in its third shell. But the sodium, having lost it, now only has nothing in its third shell, but it's second shell now becomes a valence shell and is full. It's got 10. But I now have 10 electrons and 11 protons. I positively charged. This over here has 18 electrons, 17 protons, negatively charged. And there you go. That's an ionic bond. It's just an electrostatic attraction between oppositely charged ions. And so the ions are charged particles. These are charged now that they have lost their or gained an electron, right? Okay, so that's important. There's a transfer of electrons. There's no sharing of electrons in an ionic bond, okay? No sharing of electrons. So we get a salt. This is what table salt looks like. The sodium and the chlorine ions are strongly attracted to each other. And like a covalent bond, this is also considered by chemists to be a strong bond. However, in biology, you put salt in water, it dissolves, right? It just disassociates from each other, and then you have your electrolytes. So yeah, to a biologist, we're like, disassociates in water. But the chemist, that's a strong bond. And here's how you know. You can take table salt, put a big, chunk of it in your frying pan and try to melt it and to melt those bonds, and you can't do it. Basically, you end up melting your pot almost trying to do that. Okay, now let's get to this other one. And this is a type of bond that gives a lot of people a hard time. And this is the hydrogen bond. Okay, this is a weak bond, but it is incredibly important for biology and life in general. Okay, so here's our water molecules, all right? We got our water molecules here. This is slightly negative, and this is partially positive. Now, this is not an ion, right? This is not a charged particle. It's a polar molecule with a partial negative end and a partial positive end, okay? And that, once again, is because the electrons are spending more time near the oxygen. Now, the hydrogen bonds are caused by this, once again, an electrostatic attraction between these polar molecules. And specifically, here's a hydrogen right there, okay? Those are the hydrogens. And it's partially positive charge. It's going to be attracted to this oxygen right here, which is a partial negative charge. And it could also form a hydrogen bond with nitrogen as well, if I had like ammonia in there or something. These little dots represent a hydrogen bond. They're very weak. Stick your finger in water, move it all around, you're breaking and making hydrogen bonds by the trillions, okay? Once again, this is a very weak bond, and electrons are not shared, and it can be between two molecules. You can also get intramolecular hydrogen bonding as well, which becomes very important for different types of complex sugars that we'll learn about, and protein folding. Proteins have their own shape, and hydrogen bonds can be really important for that. So, water is liquid at room temperature because those hydrogen bonds are attracting the water molecules together, okay? And that's important. And it can also dissolve other molecules in there like sugars because they form hydrogen bonds with the water molecules. Okay, now, really quickly, chemical reactions. This occurs when you make and break chemical bonds. So fire is a chemical reaction, okay? And you get this formula right here. Here's our formula, C6H12O6 plus 6O2. Those are the reactants. So this tells me I got 6 carbons, 12 hydrogens, 6 oxygens, and 6 molecular oxygen molecules. And this is my product. We're going to break it down into these smaller things, hydrogen, water, and carbon dioxide. Now, importantly in this chemical reaction, we're making and breaking chemical bonds, okay? We're not altering any of the elements, right? You cannot alter an element through a chemical reaction. Only a nuclear reaction can do that. But what we do is we rearrange these elements into new molecules. So if I've got 6 carbons in my reactant, guess what? I've got 6 carbons in my product, hence 6 carbon dioxide molecules. And importantly, It requires energy to break a chemical bond. So when you're starting a fire, you're having to add energy in there to break the bonds of the cellulose, the glucose molecules apart. And then the fire you see is the energy being released when the chemical bonds form. Okay. So this is an example of a chemical reaction, not changing the elements, but we are rearranging them into new molecules. And in the process, this particular type of chemical reaction is releasing energy. Okay. So really quickly, the life of these elements, right? I've talked about this before. I'm just absolutely fascinated at the fact that oxygen that you're breathing right now is over 5 billion years old. And it might be some that are 11 billion years old, right? They've been in carbon dioxide molecules, they've been in water, they've been in organic molecules, they've been bound to rocks. There's even been oxygen's been in other dinosaurs, and you may even have an oxygen molecule in you that was in Albert Einstein 100 years ago, right? So it's really cool that these elements just keep getting used over and over and over and over and over again, and they will be continually used for a long time. All right. Well, that's it today. These oxygen molecules and all these elements are going to last trillions of years, and they're going to have a lot more journey ahead of them. So this is the end of this lecture. Until next time, stay curious.